Hello everyone. In this video I'm going to cover the topics that were supposed to be taught on February 8th. And that boils down to other types of equations that we'll solve here in the first unit. So in order to solve an other type of equation, you're going to treat it very much like we did the square root property. And I'll explain more in the next slide how that looks and what to look for. But the process is going to be the same. So we'll isolate the weird math, which is including but not limited to some absolute value bars, or some kind of root, an expression raised to some power, which would be the what we covered in the square root property, or later on in the semester, log or exponential functions. Once you isolate that piece of the equation, you want to undo the weird math. We'll get more into that in specifics, but that's going to change depending upon if you have some expression raised to a power, or absolute value, or square root, or log, or exponential. This is where all the math happens. From there, you'll solve whatever's left over and then check your answers. Checking your answers is important as it has ever been for this lesson. Let's take a look at square root or any type of root equations. On this slide, the word I was looking for in the last one was radical. I'm going to go over radical equations. And you can see I've got two very similar examples written out here. The main difference being what number is in the root. So here we have a 3 in the root, aka a cube root. And over here, this is just a square root, and if you don't know, this is just a 2 that's in that root. So what you want to do is you want to isolate the square root. So you can do that by dividing by 5. From there, you'll see that the square root of p minus 3 equals 6. And equivalently over here, we can also divide by 5 so that we have the cube root of p minus 3 equals 6. Now I want to stop here. In both of these equations, I've isolated the weird math, right? The square root and the cube root. This is where I say, step 2, undo the weird math. It's going to be different for both of these equations because you undo a square root differently than you undo a cube root. So let's just do this, for example. You can undo a square root by squaring both sides, and you can undo a cube root by raising both sides to the third power. And how do you know you're supposed to do that? Well, it's just whatever number is in the root. That's the exponent you'll raise both sides to. So since there was a 2 here, you would raise both sides to the second power. Since there was a 3 here, you'll raise both sides to the third power. And that's how you undo this. So the square root and the square cancel, the cube root and the cube cancel, leaving us with just p minus 3 on the left side of each equation. Now the right side, 6 squared, is 36. The right side in this other equation, 6 to the third power, is 216. You can figure that out on a calculator. From here, you have to check. We have to solve. So the first equation, add 3, add 3. The second equation, add 3, add 3. And you're left with, what do you get here? P equals 39. And here you get P equals 219. The last thing that needs to happen here is you need to check to make sure the answer works. So what you do is you take your answer and you substitute it all the way back in here for P in the original equation. So you can write that down. That's a 39 minus 3 equals 30. All right. So you can just do a visual check here. 39 minus 3 is 36. So inside the square root now is 36. The square root of 36 is 6. Is 5 times 6 equal to 30? Yeah, so this checks out. And I'm going to just leave this check for you to do. You'll have to figure out how to use a cube root in a calculator maybe to figure it out. I will tell you that it checks, but go ahead and double check yourself just to make sure. For this next example, I want to take a look at this equation, x equals square root of x plus 6. And your first inclination might be to look at this and say, well, hey, it's already solved. I can see the x here. It says x equals. But the problem is this second x on the right side of the equation. This is not solved for x because x isn't completely isolated. There's one over here as well. And I didn't go over it last slide because I just kind of wanted to go over procedure. But how do you know you can use the solving technique I laid out at the beginning? Well, we can grow our concept a little bit here from the square root property. Remember, with the square root property, you had to cover up what was being squared and you could only have numbers left over. And it's not quite the same here, and I believe that radical equations are the only ones that fit this bill. But if you cover up if you have a radical at all, say this one right here, then chances are you can solve for x. You just have to make sure you isolate it and then square both sides in this case and move on and move on. When you get it back over into logs and exponentials and absolute value equations and other things that aren't square roots or cube roots, then you have to make sure you only have numbers left over. This is the only one that breaks that rule. So how do you go about solving this? First thing you need to do is isolate the weird looking math part. Yep, that's all by itself on one side. So you can start raising both sides to a power. And it'll be 2 this time because that's what's in the root. So the square and the square root will undo each other, leaving you with an x squared equaling x plus 6. From there, you can subtract the x and the 6 from both sides. And then I promise you, if you start with some type of equation that isn't quadratic and you get something quadratic, it will factor. So this does factor, so I'm just going to go ahead and say factor it. And you'll end up with x minus 3 times x plus 2 equaling 0. From here, you can set each of these factors equal to 0 and solve for x. And you'll get 2 different answers, x equals -2 and x equals +3. Now I am going to go through the formal checking process here because it's important to show you that you have to check each x value that you get. So I'm going to check x equals 3 first, which means over here in this white ink equation, I'm going to substitute 3 in for x. And hope that both sides are equal. And once you can tell that both sides are going to be equal or not, then you can stop writing things down. So in this case, I know the left side will just be 3, but inside the square root here, 3 plus 6 is 9. And I'm thinking from here, y'all can see 3 equals the square root of 9 is going to be a true statement. So x equals 3 is a good answer. All right, let's take a look at the next one. We have to check x equaling -2. So let's see, check x equals -2. So you can substitute -2 in for x. Plus 6, there we go. And so on the left side, you're going to end up with a -2. But on the right side, you're going to have a square root of 4. Now I can go ahead and tell you right now that the square root of 4 does not equal this -2. So this answer here is no good. That means we only have one answer out of the two that we got. We only have one answer, and it is x equals 3. On this slide, one more example here for square root equations. I have a equaling the square root of 19 minus 2a, and then plus 2 outside. So I see there's a square root. Interesting. Okay, so with the square root, that's the part I need to isolate. So I'm going to need to get rid of that plus 2 as a minus 2. A minus 2 equals the square root of 19 minus 2a. So we've isolated the weird math piece. How do we undo that? Well, it's another square root, so go ahead and square both sides. Now this is different from any other example you've seen because the left side, or the non-root side, has 2 terms. And I did this subtly in all the previous examples, but I didn't say it. You have to put parentheses around the entire side, then square it. So what that means really is on the left side, this is going to end up being a minus 2 times another a minus 2. Go ahead and distribute that out. You will get a squared minus 4a plus 4. And then the square and the square root will cancel out, leaving you with a 19 minus 2a. You can add 2a to both sides, right? It's quadratic. I can see a square here. It's quadratic, so I can add 2a to both sides for that to zero out. I can subtract 19 from both sides, so that will zero out, leaving me with a 0 on one side, which is what we need. And then it'll be a squared minus 2a minus 15. And yes, this does factor. So it will end up being a minus 5 times a plus 3. Great. So you can set each of these equal to 0 and solve for a this time. Oops. There we go. And so you know one answer from the blue underline, or the left factor, will be a equals 5. And you'll know the other answer from the second factor will be a equals negative 3. So I'm just going to check these. Those are our only 2 possible answers. So let's check, go back to the original white ink equation over here. Let's see. So I'll have, there we go. Something equals 19 minus 2 times something plus 2 outside the square root. That something in this case is 5. Awesome. So you can simplify this however you need to. 2 times 5 is 10. 19 minus 10 is 9. So this will be a square root of 9. Plus 2 outside, and there's still a 5 left on the left. And from here I can say these are going to be equal because the square root of 9 is 3. 3 plus 2 is 5. So this is a good answer. Hooray. Maybe a equals negative 3 will also be a good answer this time. It wasn't in the last example, but let's check. So we'll have a negative 3 and a negative 3. What happens here? This goes in parentheses, equals 19 minus 2 times negative 3 plus 2. All right, what happens? I can simplify what's in here. This will end up being, what, 25? Negative 2 times negative 3 is a positive 6. So 19 plus 6, yeah, that's 25. Plus 2 equals a negative 3. And I can see it here. Let's see. This is 5. 5 plus 2 is not equal to negative 3. Well, unfortunately, this is not a good answer either. And if it turns out that you get 2 answers like we did, and neither of them work, Like you had possible solutions, but none of them work, so then your answer would be no solution. So if ever you see that happen, if all of your answers don't work, they don't check, your answer is no solution. One last thing I want to mention about radical equations is that they don't always have to be represented to you with a radical. If you take a look here, say you have a radical with a variable being raised to a power, and there's some number for a root, whatever, b, the bth root of a to the t power. You can write this as what we call a rational exponent. And like this, the power will go in the top and the root will go in the bottom. So b for bottom, t for top. There you go. But that means you can also rewrite, because of how exponents work, taking a root is actually a form of taking an exponent. You can actually apply the top part of the exponent later instead of sooner. So there are just a couple different ways to write that out. What that means is, and this comes up very heavily in math courses, is that you can rewrite the square root of x a little bit differently. If you know, remember, there's a 2 in this root, and it has an exponent of 1. So we could rewrite this as x to the 1, because that's the exponent here, over 2, because that is the root here. So x to the 1/2 power is the square root of x. Similarly, we can do the same thing here with the cube root of x, or the third root of x. You know it's x to the first power, so you can see a 1 will go in the top and a 3 will go in the bottom. And again, over here with the fourth root of x, there will be a 1 in the top and a 4 in the bottom. The reason I bring this up is because you might see an equation something like here, let's do 4x to the 1/3 power equals 8. Sure. How would you solve this? Well, if you would just remember that anytime you see a rational exponent, it's the same as having a root. So however you would solve this using a root, you can solve it using rational exponents. So again, the first part is, this is the weird piece of math. How do you isolate it? Well, you have to divide by 4 in this case. So that will cancel out to 1, and you're left with x to the 1/3 power equaling 2. Now, you know from right here that if you needed to get the x, get rid of this cube root, get the x isolated, you would raise both sides to the 3rd power. Well, if you have this in your equation, it's still going to be the same thing, but worded just slightly different. So I'm going to raise both sides to the 3rd power, as we do, and then tell you that I raised both sides to the reciprocal power. That's what happens. Reciprocal, I hope you remember, is just when you flip a fraction on its head. So 1/3 becomes 3/1. We don't write the over 1 because 3 divided by 1 is just 3. All right, so from there, you can reduce this with this and get x equals 8. And yes, you can put this back over here into the original equation, raise it to the 1/3 power, and then multiply by 4, and it will give you 8. But I just wanted to point that out, that rational exponents are a thing. And we'll move on to the last idea here. Absolute value equations. Now, this is a different type of mathematical operator. The absolute value is different from a radical. And you can tell, I mean, it looks different. It's not the same as a radical shape. So this has a slightly different mathematical way to undo it. But here, the process remains the same. If you cover, as the square root property, if you cover up this absolute value, you only have numbers left over. Again, the only type of equation that doesn't need to meet that requirement is the radical equation. But if you cover this up, there is only numbers, so that means we can solve for the weird math. Right now, the weird math is this absolute value. So you can add 7 to both sides. That zeroes out. That leaves you with 2 times the absolute value of x equaling 10. You can divide by 5, so we're, divide by 2. We're just isolating that weird math right now. Cool, so the absolute value of x equals 5. So what does the absolute value function do to a variable or anything inside of it? Well, again, I hope you remember, I'm going to say it, but I hope you remember, it makes the values positive. So if I put any number inside of an absolute value, let's say 3, it makes it positive. But it was already positive, yeah, then it just makes it positive still. If you have the absolute value of negative 100, it makes it positive. And what happens then is every time we have a variable inside of an absolute value equation, that means it could take on 2 different values. X could be 5, because if you put 5 in here, you'll get a positive 5. Hooray! But x could also be a negative 5. If you put negative 5 in here, you'll get a 5. So the answer for this is x equals plus or minus 5. So in order to work through this and other equations, to undo an absolute value, you can drop the bars. So I call these absolute value bars. You'll notice that in the next step, they're gone. So you have to do that and put plus or minus in front of the other side. So that other side would have been 5, put plus or minus in front of it. And you can go back and do a check with these too. You can visual check it. If you put a positive 5 in here for x, the absolute values will turn it into a positive 5. Then you can multiply that positive 5 by 2 and get 10. 10 minus 7 is 3. It works out. You also have to check negative 5. If you substitute negative 5 in for x, the absolute values make it positive, so it's a positive 5. Positive 5 times 2 is 10. 10 minus 7 is 3. It works out. And this will work every time. I've got one more example to show you, and hopefully you'll believe that it works every time. So here's a slightly more difficult looking, not in actuality, slightly more difficult looking absolute value equation. So same process, make sure you are isolating the absolute value piece first. That zeroes out. 2 absolute value of 5 minus 3x equals 16. Divide by 2, divide by 2. 5 minus 3x equals 8. All right, we're going to undo the absolute value. Don't blink. 5 minus 3x equals plus or minus 8. So there it is. The last equation, it was nice because we only had a variable, just a single variable with coefficient 1, exponent 1. We didn't have to do any other solving. But when you end up with an equation like this, there's still some solving. You haven't isolated x or the variable yet. So what you have to do is you have to break it apart into 2 equations. 5 minus 3x equals positive 8, and 5 minus 3x equals negative 8. And what's cool about these is that you solve them the same way. So you're going to subtract 5 because you're trying to isolate x. Okay, that zeros, that zeros. So you're left with a minus 3x equals 3 and a minus 3x equals negative 13. And what's left? Oh yeah, divide by negative 3. Divide by negative 3. Divide by negative 3. That cancels, that cancels. So what are you left with here? X equaling 1. And for this equation here, you're left with x equaling a positive 13 over 3. Remember, a negative divided by a negative is a positive. And I'm going to just alert you, hey, these work. These answers both check. And that's it. That's absolute value equations. And the rest of week 3 material. Go ahead and finish up your assignment. I'll leave it open for extra time, and I wish you luck.